Welcome to today's Explainer. You know, it's wild to think about, but a modern enterprise processes literally millions of data points every single second. If you've ever looked at the massive landscape of technologies handling all that, stuff like cloud computing, AI, quantum mechanics, databases, and felt like it was just this giant, intimidating wall of buzzwords, well, you are definitely in the right place. Today, we're going to map out these complex IBM enterprise technologies by building a metaphorical digital factory right from the ground up. By the end of this explainer, you're going to see exactly how all these moving parts fit together to create a really powerful modern business engine. Okay, let's dive into this. Here's our blueprint for today. We'll be covering building the digital foundation, managing the data supply, the software assembly line, the artificial intelligence brain, securing the tech ecosystem, and finally, the next quantum leap.
All right, part 1, building the digital foundation. So to build our factory, we obviously need a plot of land, right? In the digital world, we rely on cloud computing. This basically means we're using infrastructure and applications online without having to actually install and maintain them on premises. It gives us incredible agility. Instead of pouring literal concrete to house these massive server racks on site, we just build our factory virtually. We instantly access exactly what we need over the internet, which saves a ton of time and massively reduces our on-site maintenance. Now, when we're setting up this cloud foundation, we kind of have 3 main ways to rent our factory space, our tools, or our finished goods. First up is Infrastructure as a Service, or IaaS. This is essentially like renting the empty factory floor and the electricity. You have to bring everything else. Then there's Platform as a Service, or PaaS, which gives developers a flexible platform to build applications. Think of that like renting a factory that already has the assembly line set up and ready to go. And finally, Software as a Service, SaaS, delivers ready-to-use software right over your web browser. You're basically just paying for the finished goods without worrying at all about how they were made. But hey, remember, underneath all that cloud magic, physical storage hardware still absolutely matters. In the data centers that are actually powering our operations, we have to choose between HDD, which is a hard disk drive, and SSD, a solid-state drive. And these choices uniquely impact our data access speeds, overall performance, and, of course, cost. HDDs are traditional and cost-effective, sort of like your old spinning CD-ROMs. They're great for cheap bulk storage. SSDs, on the other hand, are like the lightning-fast memory in your smartphone. They offer the blazing-fast access speeds that our modern factory usually demands.
Moving right along to part 2, managing the data supply.
If the cloud infrastructure is our factory floor, then data is the raw material that's eventually going to be pumped through our supply lines. And to manage those raw materials, we need warehouses. Traditionally, we use a relational database. This is a highly organized, structured way to store data in rows and columns that form a table. Think of it as a pristine, perfectly organized warehouse where every single item has a very specific, predictable shelf, which maintains total consistency and integrity for our data. But you know, what if our raw materials come in odd shapes and sizes? That's where we contrast relational databases with NoSQL databases. Let's de-jargonize this for a second. NoSQL literally just means non-SQL. It allows us to store and query data totally outside of those traditional, rigid row and column structures. So if a relational database is a strict filing cabinet, a NoSQL database is more like a massive, super flexible storage bin that can effortlessly handle huge volumes of unstructured, varied data. And this brilliantly illustrates a core challenge in data management, which is governed by the CAP theorem. The CAP theorem essentially states that a distributed data system can only deliver 2 of 3 characteristics at any given time: consistency, availability, and partition tolerance. This is the ultimate factory trade-off. You literally cannot have perfectly consistent data, absolute uptime availability, and perfect tolerance for network drops all at the exact same time. You have to choose. For example, an ATM network prioritizes perfect consistency so you don't overdraw your bank account, right? Even if that means the machine occasionally has to go offline. Okay, part 3. The software assembly line. So a quick question for you. How do we build software for this cloud efficiently? When you have developers writing code on one side and operations teams trying to keep the system stable on the other, how exactly do these teams avoid massive bottlenecks and get complex digital tools out the door fast?
Well, the answer is DevOps. DevOps acts as our ultimate conveyor belt. By merging software development and IT operations, we create a seamless flow. First, we combine our software tasks. Then, we rigorously automate testing and deployment, and this allows us to drastically speed up the delivery of really high-quality software. Instead of these manual handoffs that cause frustrating delays, DevOps creates a continuous automated loop that keeps our factory running at absolute peak efficiency.
Which brings us to part 4, the artificial intelligence brain.
So a factory running this fast generates a ton of complexity, meaning we need a really smart management layer. Artificial intelligence enables computers to basically think and decide like humans. In the context of our digital factory, this is the overarching intelligence that can parse massive amounts of inputs and automate responses. It makes our business operations exponentially more intelligent and proactive, rather than just reactive.
Now, AI is a massive umbrella, but it breaks down into a few specific subcategories. You have machine learning, which uses data and algorithms to learn over time. You have deep learning for even more complex tasks. Then there's natural language processing, or NLP, which allows machines to understand text or voice data, which is perfect for things like customer service chatbots. And finally, you have neural networks, which recognize patterns to solve common problems. Understanding this hierarchy really helps clarify exactly how our factory's brain is structured.
Let's zoom in on one of those key components for a second, deep learning. Deep learning goes a massive step further than basic machine learning because it actually simulates the neural pathways of the human brain. And this is absolutely incredible. It helps our factory systems learn to identify patterns and undertake our most complex analytics entirely unsupervised, getting more and more accurate over time. It's literally like having a factory manager who gets smarter every single day without anyone ever having to train them.
Part 5. Securing the tech ecosystem.
Here we face a really critical question. How do we protect this massive, complex digital factory from internal and external threats? Because let's face it, we are constantly vulnerable to things like malicious software, debilitating ransomware, and aggressive DDoS attacks that flood our networks with traffic just to deliberately disrupt operations. The stakes here are incredibly high.
The answer, of course, is cybersecurity. Think of this as our factory's elite digital security guards and impenetrable vaults. Cybersecurity encompasses all the technologies, procedures, and best practices explicitly designed to fend off cyber attacks. This ranges from preventing those deceptive phishing schemes that try to trick our workers into handing over sensitive data, all the way to rapidly locking out unauthorized software that tries to breach our core systems.
To manage all of this, enterprise factories use a SOC, or Security Operations Center. A SOC basically centralizes our entire defense strategy by unifying our cybersecurity technologies. It coordinates operations seamlessly across the whole organization, massively improves our ability to detect hidden threats, and enhances our response and prevention protocols. The whole goal is to ensure we catch a threat well before it ever has the chance to disrupt our business.
And finally, part 6, the next quantum leap.
Now, what's really interesting about this slide is we are entering the realm of quantum computing, the absolute cutting-edge R&D wing of our factory. This isn't just a faster computer, it is a completely different paradigm. Quantum computing harnesses the naturally occurring immutable laws of quantum mechanics to solve problems that are vastly too complex for our classical factory computers to ever calculate. It completely, fundamentally shatters the limits of classical problem solving.
To really understand why it's so powerful, we have to look at the qubit. In classical computing, data is encoded in traditional binary bits, ones and zeros. But the qubit replaces that traditional bit, serving as the new basic unit of information in quantum computing. Because of quantum properties, qubits can actually represent multiple states at once. It's almost mind-bending to think about, but it allows them to process incredibly complex, multivariable problems at speeds that seem like pure magic compared to the binary systems we use today.
And as we look to the absolute bleeding edge of our R&D wing, we encounter concepts like neuromorphic computing, which literally mimics the way the human brain actually works. I want to leave you with that awe-inspiring thought today. We've gone from just renting cloud servers to building systems that literally simulate human intelligence at the hardware level. Imagine a future where our enterprise hardware is virtually indistinguishable from biological intelligence. If our digital factories start thinking exactly like we do, what will our role be in the future of work? Thank you so much for joining me on this explainer, and keep learning.